Hello everyone and welcome to our 21st lecture, Probabilities. So this lecture will be a dump of information because my brain refused to listen and connect it coherently. So prepare for topics which follow only one logical order, and that one is lost in some 3 AM thoughts a few days ago. Let's get started with this mess of a lecture. So probability, what is it? It measures how likely an event is, or in other words, how often does it occur on average. Low probability does not mean impossible, and high probability does not mean guaranteed. Well, we'll see what does mean impossible and certain later on. Probability is marked with a capital P, and in the bracket we write the event or the name of the event with the given probability. For instance, probability of event A is 0.8 would be written as P of A equals 0.8, which means that the event A itself will happen in 80% of all possible ways something can happen. We can use any capital letter for the event markings, usually down the alphabet from A to Z. Certain letters are reserved for certain events, like E for elementary, more on which in a bit. And then, depending on your language, one is for certain events, so those that will definitely happen and have a P of 1, and one letter for impossible events, P, is 0. I will use G for guaranteed ones, so it's easier to remember, where P equals 1, and N for null, where P equals 0. So to get a probability of something, we would have to divide the number of favorable outcomes with the number of all possible outcomes to get us the formula like this. Following it, we can determine some properties of probabilities. The first one is that the probability of a single event is always between 0 and 1. As favorable outcomes cannot happen in a greater count than all possible outcomes could. For instance, a team cannot win 11 out of 10 games, because it's just impossible. They don't play 11 games if they only play 10. This example isn't really on topic, but it does illustrate the impossibility of it. The other side of the coin is that the favorable outcome cannot occur, giving us 0 divided by n, which is 0. From this we can get two more properties, or explanations to the border conditions, which will be increasingly more important as lectures progress, with further videos down the math line. If the probability of an event would be 0, it is impossible for that event to occur, and that is the only way. Even if it's 0.000000000000000, how many ever zeros you want, as long as there's some number after that, another digit that is non-zero, it is probable for that event to occur. And I will explain later in the video why that is, or give you a more real-life example. And second, if the probability is 1, it will certainly occur. There is basically no way it cannot occur unless you don't conduct the experiment, more on which again later. So for our example, let's label the event A as rolling a 6 on a fair 6-sided die and solve for the probability of it. So we get our formula, and on top of our event for favorable outcomes is rolling a 6, and on bottom it's rolling a 1, 2, 3, 4, 5, or 6. So we have one outcome on top and 6 on bottom. As we count each individual element that can happen, we get 1 over 6, which is our probability. This outcome, so rolling a 6, is known as the elementary outcome, or a simple event, or a sample point, whatever, and it is a single indivisible result. So since a simple dice throw can't be broken into more events, rolling a 6 cannot be broken into more events, it is an elementary event, which then becomes elementary outcome. I will explain the difference slightly later, because it makes more sense coherently, I think. As I said, it was lost at some 3 AM thoughts. Basically, elementary outcomes, or elementary events, whatever you want to label them, they're marked with En, so the number of it is in the subscript. In this case, E6, because it's rolling a 6 on a fair die. Hopefully this makes sense. As for a fair die, the probabilities of each throw are equal, like this. So probability of throwing a 6 is equal to the probability of throwing a 5, which is equal to the probability of throwing a 4, 3, 2, or 1, and they all equal 1/6, 1 over 6. So this is another important property, that all the probabilities for this independent event, or whatever, in an experiment would add up to 1, which makes sense as that would be the probability of landing either of the numbers on the die. and you certainly can get a 7 on a 1/3 six-sided die. This shows us that probabilities, like events, are additive, so you can add independent events or outcomes, and together they'll add up to the total probability. I will go more into the example as well slightly later, so I won't explain it as much. Now let's explain what an experiment is in this context. So, to be precise, it's a random experiment, and it is a process where the outcome is not known in advance. However, all possible outcomes are known. So you know what can happen. So for a dice throw, we know that we can throw a 1, 2, 3, 4, 5, or a 6, but we do not know which one it will be for certain. We just know one of them will be. Examples are rolling a die, tossing a coin, or drawing a card. Now, to understand more about how it all works, we have to take it step by step. Let's take our die roll example. So the topic of this slide is sample space, and it is essentially a set. So a set of all the possible outcomes. Basically an experiment set, a sample space, whatever you want to name it. It is marked as a capital S, capital U, whatever marking you use per source. Depends on your teacher as well. I think we use U, and then depends, really. And then, because it is a set, we have to use squiggly brackets when listing elements. Here on the left, I will be doing it mathematically, and here on the right, I'll do it visually, so I'll be drawing stuff, so it's easier to connect the lines between math and understanding. I think that's what I wanted to say. So for our die roll example, we have 6 possible outcomes, rolling a 1, 2, 3, 4, 5, or 6, and they're listed here in the set as the elements. So we have this. Now it's easier to see how many elements are in the sample space and everything. How would we work with that further? Well, here I included the count of elements. So absolute value of the set, or n of set, is the number of elements in that set, as I mentioned, which will help us later marking in formulas how, for instance, these are all the total outcomes. So how would you list the number of them in the denominator for the formula? Well, you use this or this. So the count of elements in the set. Just a side note to add. Great. What if the question from before was not throwing a certain number, but if we were to throw an even number? Well, then we set up a formula and mark the event A. As we said before, A before was throwing a 6, now it's throwing either of the even numbers. And to ensure consistency, I will label the throws not as numbers, but as elementary outcomes. Now, the probability would be the count of all the outcomes in the favorable event divided by the count of all the outcomes. Here it's important to introduce the terminology since I forgot before, and it makes sense now. An event is a set of elementary outcomes, meaning an event can contain one or more outcomes. If it were to contain no outcomes, we would mark it as n, or the null, since it would become an impossible event, because no outcomes in it means no probability for it. So it's a null one, and that does not have any outcomes, so we aren't really interested in it right now. As for even numbers, I marked here the subset A, so the event A, in other words, and the probability of it occurring would be 0.5 because it's 3 divided by 6. I then write out the formula. I just use this to explain the difference between events and outcomes. So it's usually elementary outcomes that comprise events. So an event is something that you're interested in and is grouped by smaller outcomes. However, they can also be called elementary events, as technically an outcome can be event, but event is a set of outcomes, if that makes sense. So if event has only one outcome, that outcome is an event. I'll try to stick to the correct terminology, but yes, event is a set, outcome is the element. If there's only one element in the set, I will call the set as the outcome, or as the element itself, as there's no reason to have 7 labels on just one item. You know, that makes a lot more sense. Anyway, there is drawing in math, and it's called Venn diagrams, especially in probabilities. They represent the sample space and all events as regions inside it, with all the outcomes as elements to those regions. They are helpful when visualizing which outcomes belong to which event and how the events overlap. For instance, as shown here, maybe quite badly, but I hope it's well enough, we have red, blue, and purple sets. The dots within the confines of the colored lines belong to their respective set. If an element is within two bounds, like here, those circled in dashed yellow lines very weirdly, they belong to a red and the purple set. So basically, if either of the two outcomes were to happen, their probability of happening would be counted under red and purple set. For instance, if the top one happens, we know that red and purple set event happened. So that kind of foreshadows certain future exercises we're going to solve in this video. But yes, it's slightly confusing, maybe for now, but you'll understand by the end of the video, for sure. There are three main interactions or relations between the events in a Venn diagram. There are others, but I won't go too deep into them. It would have been helpful if I did logic first, like the if, or, and, etc. But we can do it without it as well. So, first we have union, which means the outcomes of A or B. So the outcomes in either of them. It is marked as A union B, where this weird U isn't really a U. It symbolizes union. On our first example, so here in the top right, the union of A and B regions is colored in yellow. So the union of them represents a set in which all of the elements in either of the sets are, like here. So basically just get everything together. And this is like a mathematical way of writing it, but it's also like a symbol on its own for a set. So before we had like A is squiggly brackets elements, this stands in for another set. You could also just use one letter symbol or whatever, but this way you show that it's actually a union of two or more sets. The second is intersection. The symbol is an upside down one of the union, but I guess the computer version is stuffed so it doesn't look close to it. And the image on the top right shows that the elements in the set K are sort of utensils, while the elements in the set T, I'm guessing, are things you put in on the table for lunch. Although you could easily put spoon, spatula, and whisk for lunch, so I don't know. Take it up with study.com, they probably explain why this is labeled as it is, or what the elements represent. But we see that in the intersection, we only have fork and knife, so the yellow colored part. The sample space is labeled as U, and we also have couch and television, which fall under neither of these two. Although technically you could put the television on the table, if you really tried. But yes, the intersection basically labels only the elements that belong into multiple different events at the same time. So right here, fork and knife belong under K, and they belong under T as well. There could be a property that the intersection between the sample space and a subset would be the subset itself, but I'm not gonna go into those properties because, to be fair, everyday math does not really need them as much. And for the last relation we cover is complement. Not complement as complimenting someone, but complement, which is marked as A with a lowercase c in the superscript, or as A prime, which is what I'll be using in PowerPoints because it's a lot easier. It labels all the outcomes that are not in A. In other words, it is the difference between the sample space and the set A. With that being said, let's finally work on actual probability, how to solve problems involving them, and other fun stuff that belongs in this lecture. First step is to assign probabilities to elementary outcomes. Then we will add those in the same set for event probabilities. So we see that the first step to solving any example is to know what the probability of each elementary outcome is, and then group them together into events, and then calculate the probability for those events, and then whatever we want to know. So, well, this gives us our formula for total probability. The sum of all probabilities, as mentioned before, of all elementary outcomes would equal to 1. So all smallest outcomes that can occur will always add up to 1, or 100%. This guarantees that all outcomes are accounted for and no outcome is counted more than once. So the probability of an event A, marked here, is equal to the sum of probabilities of all the elementary outcomes which are elements of the set named A. This is the, I think, correct mathematical way to write it, and all complex. So let's see the drawing. There are 7 dots in the overall set. I forgot to mark it, but that's not important. And there's 3 dots in the set A marked purple. This means that the probability of event A occurring is the probability of either of the 3 elementary outcomes inside the purple line of occurring. And if there's only 7 dots in the entire sample space, then the probability of each dot or elementary outcome is 1 over 7. So the probability for event A would be 3 over 7 because we have 1 over 7 plus 1 over 7 plus 1 over 7. Now, what if the event is made out of a lot of elementary outcomes that may also have different probabilities? It would make calculations longer and annoying, and this is where complements come in handy. But then again, this example is not that complicated, so let's say that our event A is built from elementary outcomes 1, 2, and 3, colored yellow, red, and purple. So what would be the odds of the event A of happening? Let's do it the long way first, and then we can see the easy one. So let's do the sum. Instead of numbers next to E, I will mark them with letters, so R for red. Now I'm counting the dots with the same color and dividing that number with the number of all the dots in the sample space to get the probability. First we start with red, we have 3 red dots, 15 altogether, so we have 1/5 probability for red. Then we have 1/3 for yellow, because there's 5 yellow and there's 15 altogether. And then for purple, there's 2 purple dots and 15 altogether, so it's 2/15. Now if we add them all together, we get 3 15s plus 5 15s plus 2 15s, which is 10 15ths or 2/3, or 0.66 or 0.67 if we round it up. Now this is far from complicated and long as I mentioned it, but it's still longer to write or count than the easier step using the complement. So here's the formula for it. So probability of the complement will be 1 minus probability of A, because, well, it's everything outside of A, meaning that if we want to pick up the probability of A, we would have to find out the probability of not A, which in this case is just probability of picking a blue ball. So what is that probability? It is probability of an elementary outcome or elementary event of blue balls. If we count them, it's 5 over 15, so it's 1/3. Now, to get the probability of A, as we were interested in it, we just flip this equation on the left around by getting this one to the left and this one to the right, like so. And we just subtract the probability we solved of the complement from 1, and we get 1 minus 1/3 is 2/3. I overcomplicated this for no reason whatsoever, but that's just how it works. It's a lot simpler in reality, just write it down once or twice and you understand it. Now, there is a rule for adding up any 2 events, like on the image here. If we want to know the number of elements in the union of them, or the probability that A or B events occur, we need a special formula. Why? Well, let's see. Let's do the math for just adding together both sets, as that is the intuitive way of understanding union. The probability that an element from set A is picked on the image is 3/5, because there's 5 elements in the sample space and there's 3 in A. The probability for an event, for the element from event B is 4/5, because there's 4 elements in B. These two numbers add up to more than 1. But we know that the probability sum of all the outcomes cannot be more than 1. The problem comes from the overlap between A and B, as with the current formula we're counting the overlap 2 times. Once for A and the second times for B. So if we were to subtract one overlap, or the intersection between the 2 sets or events, we would get our formula for the union. If the events were mutually exclusive, one example is odd and even numbers, so they have no intersection, then the subtracted part would be equal to 0 and the formula is just the addition, so you can kind of see the difference. I hope this is clear. If not, please comment down below and I'll try my best to explain it so that you actually can understand it. Now, conditional probability is a measure of the probability of an event occurring given that the another event, by assumption, presumption, assertion, or evidence, is already known to have occurred. Meaning, if we know that the event B has occurred, we are looking for the probability that the event A has also occurred, aka we're looking at the probability of the outcomes in the intersection and a changed sample space. So, if the event B occurred, only the outcomes in the orange and purple area could have happened, because we know B occurred. Our goal is to know what is the probability that the outcomes that are in the purple area have happened. So let's bring in our original formula. The AB part here in the bracket just means that we're looking for the probability that an outcome from A has happened, knowing that event B has certainly happened. Now, what would our favorable outcomes be in this case? Since we know B has certainly had to happen, yellow area is out of the question. Because if an element was in the yellow area, B couldn't have happened. But if we want the outcome to be favorable, it must also be from A. So the orange part also falls out, meaning that the only part we can have on top is the purple part. Now, for all the possible outcomes, here is already the given answer. We can just say all the elements because we know that the B event has happened. So we need to know how many outcomes are in B, and that is in the denominator. So we have the count of all the elements in the intersection divided by the count of all the elements in B. So I will divide both sides of the fraction line with the number of all the outcomes in the sample space to get probabilities of individual spaces here. So let's think, when would our probability of intersection be the lowest, aka 0? And that is when B doesn't happen. And if only A and B are present, that would mean that the yellow part had to happen. But if probability of B is 0, then the probability we are solving for is impossible to be solved for, or be undefined, as we assume that it happened. And how do we usually get undefined? By dividing with 0. So that's why we can't divide both sides with all the elements in the sample space to get the probabilities of individual areas. And this is our result, because technically they cancel out either way, they're not important. So either of these two formulas is correct for solving it, whatever you're given in the given example. But yes, this formula only stakes assuming the probability of B is non-zero, and we're using it when we know that B has happened to know the probability of the intersection. Because if we don't know the probability of the intersection, we have to use the entire sample space underneath here. That is the important part, okay? I maybe made a mistake explaining the formula's origins. I low-key forgot what I was saying, but the formula is definitely correct, don't get me wrong. These two formulas are correct. But the explanation to it might not have been, but it makes some kind of logical sense. So the previous formula allows us to determine if A and B events are independent. And they are if the following is true. So that probability of A does not change if we know that probability B had happened. So if we roll a 5 on a fair six-sided die, the probability of rolling a 6 is still 1 over 6. This is what this formula basically means. So let's say B is rolling a 5, A is rolling a 6. If we rolled a 5, what is the probability of rolling a 6? If we roll again, the probability of rolling a 6 is still 1 over 6, as it was before. This means that probability of the intersection is product of them. So basically, the probability of a certain event does not change if something else had happened, which cannot be said for dependent events, because the opposite states that the events are dependent if this is not true, so the two sides are not equal, meaning that if some event has occurred, for instance drawing a card, the probability of drawing a different card after that is different. Why? Because we are not replacing the previous card in a finite set. So let's say we have 54 cards. The probability of drawing a first one being King of Spades is 1 over 54. By drawing the second card, if the first one was not King of Spades, the probability of King of Spades being on the second is only 1 over 53, which is what can help you in gambling on cards, card counting, blackjack, or whatever you want. So this is important thing to separate about probability when solving examples, that you have to know when the events are dependent or independent. So independent are when the set is not changing, so dice rolls or coin tosses, but they are dependent in a card deck where when you draw a card, you change the number of elements in the set. Hopefully this is clear. Which brings us to our multiplication rule. So the general rule for probability of two events happening in a row would be the probability of A and probability of B if A has occurred. Now, for independent events, which that I have said before can be added together to form a one or a sample set probability, if you multiply them together, for instance, a dice throw, let's say throwing 6 2 times in a row, it would be 1 over 6 times 1 over 6, because the probability would not change. So the second 6 is equally likely to happen anytime you throw the dice. So it would be 1 over 36, so this probability would not change, which I will display the formula later. However, this applies primarily to the dependent events. Why? Because let's say a deck of 54 cards. Probability of A, let's say drawing an ace of spades, is 1 over 54. And if it does come true and we drew an ace of spades, the probability of drawing ace of hearts, maybe, so ace of spades and ace of hearts in a row, the probability of drawing the second ace of hearts would be 1 over 53, because we assumed we drew the right card, and there is one card less left in the deck, so the probability of drawing a specific card gets higher, which is helpful in gambling, because the smaller the deck gets, the more likely the cards that have not fallen out yet are to appear. Or to be fair, all cards are equally likely to appear in a deck if it's fairly shuffled and not preset, but we assume that casinos and everyone conducting such gambling games are fair, which you have no way of knowing other than speculation. So here's the independent case formula. So we see that for dependent, well, this is the general rule, and it stays the same for dependent events, while for the independent, they just change this part to this, because the probability of B does not change if we know that A has happened before. Now, as for dice throws, this image here, it's very poorly said. We multiply the probabilities, which do not change. The probability of throwing a 6 is not dependent on what number we threw before, which means that it's equally likely to have a coin flip, for instance, go heads, tails, changing each throw for 1,000 throws in a row, than it is to have 1,000 heads in a row. However, the overall ratio of heads and tails throws will tend towards the first example, making it more likely as we increase the number of throws, which is kind of counterintuitive for 1,000 heads to be equally likely as 500 tails and 500 heads, but it is. This image shows permutations of two dice throws and the sum of the two dice throws, and they form a pyramid. So basically, what does it show? If you throw two dice, the results are marked by the sum. So if we throw a 3 and a 2, the sum is 5, it gets placed here. This image shows all 36 possible permutations. Or is it variations? I forgot which one. I think it's permutations. And we see that the sum of 7 is the most likely to happen. You see down here are the sums. So while, yes, 5 and 6 are equally likely to happen as 3 and 4, so let's say you're playing Monopoly or something, and you throw two dice, you're equally likely to throw a 5 and a 6 as you are to throw 3 and 4. However, you're more likely to throw a sum of 7, so a 6 and a 1. So if you want to have some strategy, the most common throw that's going to appear in the game is 7. So if an enemy is 7 spaces in front of your property, it is recommended you buy the house before that, so they land on it more likely, because you can see here, there's like 6 outcomes that add up to 7, there's 5 that add up to 8 and 6, there's 4 that add up to 9 and 5, there's 3 that add up to 4 and 10, etc. So this is just the distribution. I think this is binomial distribution, I don't know anymore, but that's not important. So as we're on topic of binomial and binomial coefficients from last time, here is a formula with many great uses. It seems kind of complex, but let's look at it on an example. First, each factor has a clear role. The coefficient, binomial coefficient, states here for arrangements or combinations, like we learned last time. The x to the power of k is successes, so the probability of favorable outcomes to the power of times it happens, and a to the power of n minus k, which could be rewritten as 1 minus x, altogether to the power of n minus k. A here stands for probability of failure, and n minus k means exponent of how many times we fail. So that equals to probability of x event, and this is also something that's going to come in handy later, so let's just omit this for the formula in example, which is, we want to know the odds that in 4 coin tosses we get heads exactly 2 times. Well, let's get our formula here, and I will remove the sum part because there's only one probability, not dice throws or whatever. If we were asked for instance, dice throws, if we had like 10 dice throws and we wanted twice to roll a 6 and 3 times to roll a 5 or something like that, we would use some formula, but because there's no multiple different favorable outcomes, we only use the normal formula, so one term. Now, let's insert the numbers. N is the number of coin tosses and K is the number of heads. Now, the probabilities, since there's 2 sides on a coin, the success has 50% and failure has 50%, so 1/2 for each. Now let's open the binomial coefficient into a fraction and multiply it with both of the halves squared. I already went ahead and cancelled out the common factors, so the 2 factorial from top and bottom, being left with 4 times 3 on top divided by 2 factorial. So I just cancelled the 2 on both sides again, we're left with 2 times 3. And then we have 1/4 times 1/4, which then again is on the left 6 times 1/16, which is 3/8 or 37.5%. Funny, right? You could also write out all the permutations like heads, heads, tails, tails, and heads, tails, etc. and count all where H appears exactly 2 times and count all possible permutations for 4 coin flips, or use math like we did here. Next is Pascal's triangle. More of an honorable mention than a part that you would need to know, but you're more than welcome to read on it, as it is quite an interesting topic. Basically, it is a triangle where each number is a sum of the 2 diagonally left and right above it. So we see the 70 in the center bottom has a 35 left and right on top of it. Then the 35 has a 20 and a 15 above it, etc, etc. Using the previous formula, one here, if you insert the number of the row as n, you will get a polynomial. The numbers multiplied to variables a and b, so the factors are the ones in the triangle in that row. Don't worry, we don't insert anything as a or b, so just look up the factors in front of them, and the triangle could help you predict what the polynomial with short notation sum of a and b to the power of 4 would look like, and it would look like this. So we see that exponent on a is reducing by 1 each next term, and exponent on b is increasing, and the factors, which I colored green, are following the purple circle pattern. Now for why this is here, because these are a and these are b. Oh, sorry, this should be an exponent here. We see that the binomial coefficient is the one that determines these places. So if you know 4th row, 3rd place, binomial coefficient would be 4th row is here, 3rd place is 3 minus 1 for k. It would be 4/2, which is 6. Simple, right? So we can use binomial coefficients to predict positions in a Pascal triangle, or to predict the polynomials of nth degree. Basically just factors in the polynomials, and then insert a and b for whatever value you have. But like, this is a very interesting topic that you can go read up on by yourself, because I think it's quite interesting to me, at least, and I'm not really that into probabilities and everything, and I don't like complex long writings, but this does seem, the more you read on it, the more fun it might get. Now for an example of some more complex probability that is still from everyday life, let's say you have a group of 5 people. What would be the probability of, well, that if these 5 people are arranged in a certain order, what would be the probability of person A and person B standing right next to each other? This is why this lecture today is after combinatorics, because that's where they come into play. So let's try and solve it. Purely as an example, this falls slightly outside of my purpose here, as it is technically a basic problem on probability, but its difficulty might be a bit too hard for some that aren't math savvy. So this won't be on the mini test, but I still show it for those that are interested in it. So I list all the people here, and I drew all the places that they can take if we order them. We know from the previous lecture that the number of ways 5 people can be put into a specific order is 5 factorial. So 5 times 4 times 3 times 2 times 1, which is 120. So there is 120 possible total outcomes for our example. Next, if we want to count favorable arrangements so that A and B are adjacent, to make this easier, we can treat them like a unit, or that they count as a single entity in the order, which means that we're essentially counting permutations of 4 objects, AB, or AB, C, D, and E, giving us 4 factorial. This isn't all. A and B can be arranged as AB or BA, so they have 2 internal permutations, which means that we'll have to multiply the favorable outcomes with 2. Just like we had 2 extra hats with all the possible combinations of clothes, you would multiply that all by 2. Here we have 2 internal permutations, so another double to the possible favorable outcomes. Yes, this accounts for all the rearrangements within the block, all the positions that the block can take, and the permutations of all the 4 elements. And this gives us 2 times 4 factorial, 4 factorial times 2 as favorable outcomes count. Now we just put them into formula. We have 4 factorial times 2 and 5 factorial. We get the formula. I labeled the event of A and B being adjacent as event O, and the probability of it will equal to 2 times 4 factorial divided by 5 factorial, and we can simply simplify the fraction by cancelling common factors, which are 4 factorial, and we're left with 2 on top and 5 on bottom, which is our probability. So anytime you were in school and you were asked to pair up in your class at random, you could use your own numbers of students in the class and friends you have to see what the probability would be to get paired with your friend. Now, for homework, I recommend doing it for 10 people, and you want to know the probability of being next to either of the 2 friends. So there is 10 people in the group, 1 of them is you, 2 are your friends, and there's 7 random people. You want to know how probable it is that you will be standing next to at least one of them if you're put in order. Okay? So put 10 people in a line. What is the probability of you being next to at least one of your friends? If there's 2 friends and 1 you. Okay? Do this for homework to help you reinforce this. If you want to reinforce the advanced knowledge and actually learn more, I recommend it. Now for the mini test, this was it for today's lecture. Thank you for staying with me through this long mess of info dump and 7 retakes because it's 2 AM and I can't do it anymore. As my final thought, as I give you the mini test, just because something has a low probability, it does not mean it won't happen. If there are 10 to the power of 10 outcomes, and we assume that all have equal probability, which very often they don't, in real life especially, each would have about 1 times 10 to the power of minus 8% probability, or about 0.000000001%. But just because it's nearly 0, it doesn't mean it won't happen, as one of them has to happen if we conduct such an experiment. And fun fact, in your everyday life, there are multiple events, I'd say confidently say hundreds of them, with much lower probabilities happening all the time, always and everywhere. So don't fall for the typical argument, oh yeah, with such a low probability, it's very unlikely this would happen. Don't count on it. Something has to happen. And you'd be surprised how often low probability events can happen. So always be prepared for everything, they say. If you've made it this far, thank you and have a happy and successful new year filled with lots of math and physics and chemistry and science and everything and learning successfully. And I'll see you all on our next quest. Bye.